Hey, can you see the full screen of the presentation?
Yes, that looks good.
Okay.
I'm just going to turn off, good. Turning off permissions. All right, great. Well, welcome everyone. We are very excited to have our AGU Geodesy Early Career webinar today. It's a little inconvenient for time zone wise, but so we're so glad that Brahma has stayed up late for us today. He's talking to us from Bangalore, India, where he is an assistant professor at the Indian Institute of Science, working in the Interdisciplinary Center for Water Research. He received his PhD at the University of Stuttgart in Germany in geodesy in 2017 and had previously received a Bachelor's of Technology and Master's in 2010 and 2012. He also spent some time as a research fellow, a postdoc, and a Marie Curie fellow at the University of Bristol. And he's also the recipient of the 2023 European Geosciences Union Early Career Award for Geodesy. So we're so pleased to have you today. And he'll give a talk for about 45 minutes, and then we'll open it up for questions after that, and we'll allow you to unmute and ask questions in the chat. So please get started. Thank you so much.
Thank you, Matt. Thank you for this invite. It's an honor for me to talk in front of all of you and share some of my experiences. So when Matt invited me to talk, to the AGU folks and probably so many geodesists all around the world, I started thinking that about my journey, what I have done. And I have seen that over the years, somehow I've always pushed for geodesy as a tool, as an ally for hydrology. So I thought, why not just talk about how geodesy has been helping hydrologists and in what sense to measure the unmeasurable otherwise? Because there are certain variables which we would not even be able to comprehend their variability if it was not for geodesy. Yeah. So I'll just break this talk into its components. The title can be broken into various parts, like we decompose time series in geodesy. We can do the decomposition of the title. I'll first talk about first hydrologist, right? Why I'm talking about hydrology? So this is a definition I took from USGS, and as you can see, it's a science which tries to understand the complex water system of the Earth. Earth is a blue planet. It has lots and lots of water, right? And yet we say it's complex water system. And why? Because most of the water that we have is in oceans, majority. I think this is a textbook thing. I took it from IPCCR6, but 97% of the water on Earth is in the oceans. It's saline. And then we have saline groundwater also. We have fresh water also, and fresh water is less than 2%. Yeah. Now, I really want everybody to think here. So we all know that the water availability is a problem. Sometimes we get more water, sometimes we get less water. Imagine you get 10 buckets of water each day, and someone tells you that, well, from tomorrow, maybe I'll cut down 2 buckets. I don't think anybody would be happy, isn't it? And this is what we have seen from IPCC reports. I'll go to that point again in one more slides after a slide. Yeah. So this fresh water that we have, it's not like everything is flowing to oceans, and obviously it gets renewed and replenished via the water cycle, right? So this water cycle, again, a very simple schematic diagram from again taken from IPCC. It consists of, first of all, major fluxes such as precipitation, evaporation, runoff, discharge, you can say. But then there is some stored, which is the groundwater. I think which is one of the most valuable resources we have. It is this particular section of the water system defines the resilience of a catchment. It actually it can determine the socio-economic security of a region, of a country, of a community, and so on. It's one of the most important resources, I would say. Okay. But we know that, okay, that's land evaporation is there, land precipitation is there, and river discharge is there, right? Now, we all know that IPCC AR6 also said that the availability of water, or let's say even the flux through which the water comes to land is precipitation, and it it is supposed to change in response to climate change. And this on the slide you can see it's a multi-model seasonal mean precipitation percentage change. Yeah. And you can see the scales right down. It goes from -50 to +50. Now I'll go back to that point. 10 buckets, 2 buckets, right? You have 10 buckets, and somebody tells you, well, you'll get 2 buckets less from tomorrow. That's 20%, isn't it? And nobody was happy. Look at the scales. In some regions, actually, it could be even 30% or maybe touching 40%. So when I tell you that 4 buckets are going to go away, I think that should panic you. So this is why I think understanding water systems, the hydrology, and its response to changing climate is at the core of, I think, ensuring that we all have a sustainable development in the future. The adaptation to climate change, everything revolves around the water cycle right now. And we all know why this will happen, right? So the climate system itself is changing a lot. So there is a lot of uncertainty, right? So these are large scale circulation projected changes and their effect on the water cycle. We have poleward expansion of headly cells, polar migration of storm tracks. Then we also say ITCZ itself will move and it will get narrow and might have higher intensity. This means the tropical system, we are not even sure what's going to happen, to be honest. The confidence is low, but we know it's going to change. So the scales that you see on the left, -50 to +50, if you are seeing some region that, okay, yeah, maybe it's just 10% for me, actually, you can't say that with full confidence. It might be actually 20, 30, and 50 can go to 70 also. Yeah, in either direction. And with the urban floods, with the upcoming higher intensity of downpour that we observe, that we witness, that leads to a disruption in life in terms of urban flooding or even natural flooding, coastal flooding. Um, I think more water is also not a good news. So we want to maintain that balance, right? Okay, that was just a natural part, the climate part, right? And I think in the last 20, 30 years, humans have become so much capable of intervening with the natural system that we are talking about the Anthropocene in hydrology right now, which is a human intervention in the hydrological system on the water cycle. To just tell you what I mean by that is I'm going to tell you, I'm going to show a land use map of India because I'm from India. I want to take an example out of it. And actually, this example is very famous now. All the yellow regions are agricultural regions. Yeah. This is the water table depth. Anything red is very low water table. So we already know northwest of India is having a lower water table. And then people have used a lot of groundwater for irrigation. And which is why the famous Rodel paper in Nature in 2009 showed that Northwest India is struggling with a severe water depletion problem. Now that news came in, and immediately people said, yeah, we understand groundwater is depleting. And the next question was, at what rate? How bad is it? What are the socio-economic impacts? And obviously, the governments were running around talking about policy reforms that may help. And then there are people who would also argue the other side. Like, yeah, it is complete. Is it completely anthropogenic? Are we not able to recharge at a good rate? What is happening to the system? And to answer all these questions, what we need is accurate observations of changes in the total water volume. Yeah, I want to emphasize again volume, right? Okay, so water volume, it's a physical dimension. You need to have area and water level, and you can give some volume using some relations. In situ observation network is the traditional way of doing hydrology. You install gauges, either it's for runoff or discharge, and sometimes even for precipitation and so on. So you want to measure it, but to have an extensive network so that we can understand, because again, the question is about the global hydrology as well, not only local. It is way too costly and politically sensitive. We already know that certain countries, they do not want to share the river discharge data openly because they have transboundary rivers, right? So it's a sensitive matter. But for science to advance, we need this data. It's just not available. And I think with the advent of satellite age, we were always excited and sure that, well, active and passive remote sensing might help. But they only provide a partial solution because they only monitor the surface. And sometimes they're not even measuring the variable itself. They're measuring something else, which needs to be inferred or converted to the variable of interest. And all these things creates or require certain assumptions. And then therefore there are certain uncertainties, sometimes higher, sometimes lower. Yeah. So they provide a partial solution, right? Okay, I think we all would agree that water volume is proportional to water mass. And then there was a genius who told us that actually this mass is proportional to gravitation. Yeah. And in 1970s, in the US, actually, there was a big school wherein there were deliberations about launching a GRM, they call it Geopotential Research Mission. And using this mission, they wanted to just for a year. It was a lower orbit, very similar to Grace satellite mission. That you have two satellites, you measure the distance change between them, and you try to understand the annual water cycle just for a year because the lower in the orbits, it will die sooner. Yeah. So this concept was there and has been going around, let's say, going around the scientific community for very long. Yeah, in 1970s. Yeah. So people understood that okay, observing changes in gravity can help us monitor changes in mass. So now from this slide till now, the story says if I can measure my geometry and gravity, then I can actually talk about monitoring the hydrosphere in probably its totality. And 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 now I'll go back to my title slide again. This was about hydrology. This is where we are. We want to have improved data. We want to have better data. And I want to come back to that the first term, geodesy. How geodesy has been helping us. So geodesy is actually the science of measuring and understanding the spatio-temporal variability in geometric shape, orientation in space, and gravity field of the Earth. So I think they are kind of made for each other, right? Yeah, and there are multiple missions right now in terms of satellite. So the picture you see is for satellite geodesy, but geodesy is not only about satellites; it's also about in situ measurements, and no, it's very very old science, more than 2,500 years old now. And yeah, so we have geodesy, and that's the definition of it. So somehow it's the perfect fit. Okay. And then the last term, measure the unmeasurable. I think it's very, very important to understand what I mean by that, right? Okay. So the holy grail in hydrology is the water budget. It's a simple input output relation that whatever comes in, the total mass has to be conserved. So the precipitation is the flux that provides water to the terrestrial system. And then this is further decomposed into total water storage change, evapotranspiration, and runoff. Yeah. And there's the equation, the water budget equation. And one of the famous exercises, you want to close it. So you want to know how much came and where it went. That's it. But it's not that easy, right? Especially to do at global scale. Maybe over one, you have a sample catchment where everything is perfect. You have the perfect data. Then you can probably do it to very high accuracy. But let's look at the state of runoff because we again the context here is we also want to understand the impact of climate change. How it is tampering our water cycle. So you look at runoff, right? Okay. Now this is the state of in situ gauges in 1980 and in 2009. And I think you can appreciate that a lot of gauging stations do not provide data now. They're not active now. Yeah. So the data that is available, or that is at least measured, not even available, I would say. This is the data that is measured and basically available for us to do science has reduced significantly. You know, um, and there would be certain regions where the data is measured but is not available to us at all. So it is basically some of the data set are actually some of the basins, they have data gaps. The data quality is another issue. So measuring runoff itself is a problem. People, what you can do is you can use remote sensing. Altimetry, which is again a geodetic tool, has been a great ally, I think, in that. But again, people have developed a lot of models, empirical, conceptual, physical, for modeling runoff, and they are also popular. But again, having something observation based is good. Problem with models are if you use, because if you're an empirical model, they usually are not able to tackle the non-stationarity and things are changing. So that is one issue that you face. Physical based, there are the whole system is so intricate and complicated that sometimes the relationships they also change from in space and time. So again, there are many assumptions, first order, second order, and so on, that you must tackle first. So it's a big exercise to have accurate measurements, right? ET, another term, evapotranspiration. It is the most notorious one, I would say. Now, this is a map of in situ measurements from FluxNet sites. And you can see the green dots are only 4 years in their age. Some of them are 20 years, 20 plus years. But look at the global coverage. It's not even, I would say, 25%. Africa, the largest continent. I mean, first of all, this projection is not good enough to tell you the right proportions, but still, Africa itself is like, a combination of four or five, three or four continents, and it's nothing is available there. Yeah, and then look at even Asia. Asia is very, very sparsely. I think the best part is that over the US, not in towards Canada also, it's probably poor, and in probably in the Texas and Mexico region, but still US and Europe are doing a better job. Still, we are far away from anything perfect. And then you can also rely on remote sensing again for the same thing. And there are several methods. Yeah. And remote sensing has advanced a lot for EVT, but still I would like to borrow your attention for this slide. And this tells you the potential, not even the actual, the potential evapotranspiration obtained from four different methods of remote, and that they all use remote sensing, right? And look at these scales. I think in many places, they do not even agree with science. Not even science, they all are positive, but in the sense that the colors, it's extremely red or blue. They do not match at all. So a difference of, I would say, of a few hundred PET, let's say even 1,000 would be okay, annual PET, right? But this is just yeah. Sometimes you look at the gleam tetraset has nothing red, but look at mod 16, it has so much of red. Yeah, so it's the most uncertain component of the water cycle. So now what geodetic observations can do, right? So this is a famous, I think, method which many, I think I've seen the list of speakers in the past AGU webinars. Many have talked about the role of GNSS in studying hydrology, and there it is. So basically, you study the deformation as measured by a GNSS station, and you can always try to track how much mass change has happened in its vicinity using Green's functions, Loveload numbers, and then that can tell you, or that can help you estimate the water mass that came in the system and then went out. Yeah, that is one thing. For example, in this case, they have looked at the drought in California in this paper by Gian et al. In 2022, and it captures really well the drought conditions. Now, similarly for runoff, altimetry, like I said, altimetry does a very good job, and therefore altimetry based methods have been improved a lot. The only problem is that at present, the traditional altimeters, they are not able to monitor small streams. And I think with SWOT mission, this problem will go away. So we are very, very, very much hopeful in the future. And then I'm going to talk a lot about GRACE and GRACE follow-on because it has been my bread butter. I did my PhD concerning GRACE data processing and so on. So what is GRACE follow-on, right? They are a couple of satellites, a pair of satellites, 1 and 2. They're moving in a near polar orbit with a separation between the two satellites being 220 kilometers at an altitude of 500 kilometers. And by measuring the changes between the two satellites better than the width of your hair, yeah, that's a micrometer precision, we are able to map the gravity field of the Earth. To what accuracy? I'll just talk about it. Yeah. So there was GRACE mission that started from 2002, ended in 2017, and it just gave us enormous information and amazing results. That it was basically yeah, I think it was important, and also everybody acknowledged that there should be a follow-on mission. So there's a follow-on mission. In fact, there are new missions that are being developed to even improve what we get from GRACE, and they would be launched in the near future. Yeah. Okay, so like I said, a bit of hair and all that, but to map the gravity field of the Earth precisely. And when I say precisely, what I mean, so let's say wherever you are right now, let's assume the gravity value is 9.81270583, this so on, right? So the second place after decimal talks about rotation and ellipticity. The first after decimal, that 0.8 is the gravitational attraction, and so on. The oblateness also, right? And so on. If you go further, you will see after eighth place after the decimal, that is 1, 2, 3, 4, 5, 6, 7, 8. Eighth is polar motion and hydrology. And GRACE has been used for hydrology. So imagine somewhere 500 kilometers away from the surface, there are a couple of satellites that are measuring the value of G accurately to the eighth place after the decimal. I think this is just mind blowing. Okay. How does it work? Again, there are many, many amazing videos and animations available at NASA and all, but I did that animation myself. So I'm always somehow, pulled to show this to everyone. Let's assume these two satellites are moving in this orbit and they pass, right? So when they're in the vicinity of this lake, small lake on the right hand side bottom, let's the distance be rho L1. And when they are close to the mountain, let it be rho M1. Now, based on the distance distribution and everything, let's assume they have this distance rho M1 and rho L1. No comparison at this point in time. What happens is before the next pass, there's a huge snowfall event and there's a sudden mass increase near the mountain. So when these satellites pass, this extra mass will pull the satellites and rho M2 will be less than rho M1. While rho L2, assuming they're far away, doesn't get disturbed. Yeah, rho L2 is equal to rho L1. Now sun will come out, and then the snow will start to melt, and it might just naturally go and fill the lake. So there's a mass increase in the lake. Next time, rho L3 will be less than rho L2, and rho M3 will be greater than rho M2. So by looking at the changes in the distance, we can actually map the mass change near the surface of the Earth, right? So basically, there's a couple of satellites. You get the data, but the data is very noisy. Yeah, so you must do some post processing. That is something I tried to develop something in my PhD, a better post processing strategy. And then what you do is you zoom into your region of interest, you aggregate values. Again, because you may sample GRACE data at higher resolution, but actually GRACE native resolution is bounded by its distance from the surface of the Earth because potential is inversely proportional to the distance from the center of the Earth. And the farther you are, the coarser the resolution would be. So you can't help it. So no matter what resolution product you get from some website, the native resolution is close to 3 degrees or 300 kilometers. Yeah. So you must aggregate so that you have multiple pixels, so that noise also cancels out. Okay, and then you do that for each time point. So you get a time series. Now, by looking at these time series, you can try to understand the various natural phenomena. For example, in this video, you can see melting of Greenland. There is secular trend. And you can see the California between 2006 and 2010, there was a steep decline, and the internal variability is also there. Amazon water cycle, it's very nice. It's there are obviously some years with higher amplitudes, but you can see very smooth up and down. And then in the India also, the northwest of India, where the water abstraction is a problem, the groundwater chain. Yeah, so this is what you can do with GRACE. And it has found application in glaciology, solid earth science, oceanography, because people are also looking at sea level rise, sea level budget, and so on. So I think I would say most of the earth science disciplines have used GRACE. Yeah. Okay. What it gives you is total water storage. Yeah. This is what hydrologists love. So if you go to a hydrologist, they're like, okay, what is the variable I'm going to get? And remember the budget equation, it is TWS. Yeah. What is TWS? It is a sum total of all the storage terms near the surface of the Earth. So whether it's in snow, soil moisture, surface water, vegetation, I mean biomass, and so on. Yeah. They all form this TWS, including groundwater, right? So if I take the surface waters such as lake, rivers, near surface water storage, and groundwater and combine it, I get TWS. But if I want groundwater, I must remove one and two. So basically, the near surface water storage from soil, root zone, and so on, and from surface water, that is lake and rivers. If I remove that from GRACE, what I get is groundwater, freeze layer. So you can use this TWS budget, I would say it's TWS budget equation, to actually account for groundwater, which was great, which has been done even for India, right? Okay. Prior to GRACE, TWS was only available from model simulations. Yeah. And Earth observations have written, to be honest, but it's very hard. You may use a gravimeter somewhere in situ and then you try to understand, but yeah, it was a very hard task, especially because you can always talk about the change, but there was so much of noise when you are at the surface of the Earth. So other process must be accounted for. Okay, so this is TWS. And there are various TWS products. Like I said, prior to GRACE, models were the only source. And most of the models assume that long-term change in TWS is zero. Yeah. So there's basically, in a few years, the total water storage, if you sum it up all the values, they become zero. Yeah. Which, believe me, is not the case now. So various TWS products models are there, and then there's Grace. For example, this is level 3 Grace data from Gravis or from Potsdam. And there are also mass cons, which are highly resolved and sophisticated Grace products. And one of the issues that have been raised multiple times is that agreement between model and Grace is actually not good. So if we are using models, then we Grace, Grace varies a lot, and Grace is much more reliable. So basically, what I want to point out from this whole discussion is, if you go prior to the Grace era, that is prior to 2002, my models, which would produce some TWS, were actually insufficient. They were not good enough. Okay, so geodesy has been helping hydrology how? Using Grace to detect groundwater loss. For example, I again go back to the India example, northwest of India. And there was a paper, I think, scientific reports, and it was a good paper because it actually questioned again what was published by Rodel, that have Grace satellites overestimated groundwater depletion in the northwest of India. So they say that there have been multiple studies since the 2009 Nature paper, and due to different filtering and different correction approaches, or the way you handle Grace data, you're getting various values. For example, Rodel is 4.0, and using the well data, they achieved 2.8. And I remember the literature, the values will go from minus 1.5 to 5 point something or 6 centimeter per year. So it's a huge range, right? It's not just a little bit. So crossing Grace data, like I said, is an important step. Yeah. So these are, if I simply take level 2 Grace data and I plot it, this is what it's gonna look like. And you can appreciate that you can't make sense out of it anyhow, right? So therefore, we must filter. Filtering is inevitable. Once you filter, it reduces noise, but also it affects the signal quality. Because it's like when you smooth, you also lose some resolution, and there is an attenuation of the signal. Yeah. So these things actually can lead to an attenuation of the trends, and so on and so forth. And if you correct with a method that is not good enough, then you might have some spurious or some artificial trends. Yeah? This is what has happened with all these studies. Yeah. Okay. So the method we developed in my PhD, it kind of worked well because it was a data driven. It did not depend on any model. And actually, when we applied it over the same region of interest or the same period of in time interval, we got 2.9 plus minus 0.1 centimeter per year. And the NC2 was 2.8. So we were confident. The main message here is that if you do Grace right, actually it's a great tool. It can capture the reality very well. The California drought, I think people in the US would appreciate this really well, that in 2011 July, this was the state of the Lake Oroville. And in September 2014, this was the state. Yeah, the same bridge. And the loss of water was unseen, I would say, yeah, for decades. And if you look at Grace, again, it tells you a clear steep decline. You can see from 2011 onwards, there was a steep decline in the water storage, total water storage. And you can also compute, how much volume of water you have lost, because you know the density, you know the mass change. So you can easily get how much volume has been lost, right? And yeah, there you go. There's a California drought monitor that uses multiple data sets, and it kind of gives you warning when the drought is severe to abnormal and so on. And it matches very well even with the Grace analysis. Yeah. Okay, so these were a few examples wherein Grace was used to understand groundwater, to understand droughts, and so on. Now, coming back to the holy grail in hydrology. Yeah. Like I said, prior to Grace, TW was either zero or from models prior to 2002. So if you go and read papers from, let's say, 1990s on water budget, you would see precipitation is basically written as E plus R. The total water storage term is neglected completely. Yeah, in many and many publications, right? So, but Vigil, the situation has changed. Now we have runoff, like I said, from various models, from various techniques. Evapotranspiration, we have a whole bunch of models and bunch of estimations from remote sensing. So global total water storage we can get from Grace or models. If you're not a fan of Grace, you can also use models. And then precipitation, GPCC, IMD, CPC, ICI. So there are huge number of precipitation products as well. So what people have done is, because if you can close the water budget, if you can account for precipitation from these total water storage change, evapotranspiration runoff, then you have much more confidence in your data set. So what people have done, they've taken it as a grand challenge to close the water budget. And believe me, it's hard. So in Lehman et al. 2020, we used 11 precipitation, 14 evapotranspiration, and 11 runoff products. And we got 1694 combinations. So that means for a catchment, you can use P, ET, and R. So P minus CT minus R to get your DS by DT. And you can have 1,694 values, using these combinations. And it's up to us to judge, which combination works and so on. We also try to use often climate classifications, and this was the maximum NSE. So good thing was one of the combinations would close the water budget. You can see the NSE is mostly positive. Actually, they were all positive because you're talking about maximum NSE out of 1,694 combinations. But these combinations, so one combination might work for one basin, but that same combination might not work for the next basin or the other basin. So there was no clear winner, right? And if you use just one, for example, in this figure, on the topmost, if you use just ERA 5 precipitation ET and R, you can see now the NSE values have dropped, right? They're not as good as they looked in the previous figure. So there is no clear winner. So closing the water budget is still a grand challenge. Yeah, it has not been solved. But if let's say you have a setting where you know your ET, you have measured your ET, you know your runoff, or there is no runoff. For example, the case of Lake Urmia, which is an endorheic lake, so everything flows into the lake, and you know your precipitation very well with the gauge data. So there is the uncertainty in your data products is low. Then actually you can do a good job. So we did this with Lake Urmia, which was losing its mass like anything. It was becoming the next RLC case. And you can see in 2000, and in the bottom panel, in 2000, how the lake area was and how it declined till 2015. Yeah, it's not even half of it now. And that then you can also look at, so in the plots, you can see the blue is lake surface area, and in the green, it's the in situ water level. And you can see water level also declined steeply. Yeah. So there were some attempts to kind of, these events, A, B, C, D, E, F, G, they all are different events, sometimes drought, sometimes refilling, sometimes releasing water from reservoirs to fill the lake, and so on. And they all were captured in altimetry data as well. So that's amazing, first of all, right? Altimetry can do an amazing job. So another, I think, advertisement for geodetic technique for hydrology. And then, okay, once you know this is happening, the next question is why and what is causing it, right? So this was also analyzed. And GRACE could help us because GRACE also captures groundwater, right? So this is another plot. You can see the drought phase in yellow and the comparison between GRACE at groundwater level. So after removing basically, surface water and so on. This is the middle plot. And you can see they match very well. So the GRACE based groundwater is actually quite meaningful. And you can also see that in the top plot, the WGHM is not doing a good job because WGHM deviates from GRACE. WGHM is a model, and it was not able to capture the trend in groundwater depletion. And the last plot, the third plot, the bottom plot, is actually a water budget. Now see, there is no runoff, so R goes out of picture. One variable less. So uncertainty from that variable is also not propagated. So P minus CT is the only budget that you need to match with DM by DT. And it matches very well, especially up to till 2015, till when the GRACE Health was in its supreme. But I think around 2015 February, there was a battery failure and all, and that kind of led to higher errors in GRACE after that. But till 2015, it does a fairly good job. So yeah, that's another advocate. For using GRACE in understanding hydrology and maybe where it is coming from. So ultimately, what the whole picture was, groundwater level depleting due to agriculture, was also pushing lake water level to a lower level. And obviously, climate was also one of the factors that they also found out that less precipitation also contributed a bit. Okay, so water budget, you can try to close it. You can study it. It can be a subject in itself, but you may also use it as a tool. And I will give some example for that. Yeah. So validating model outputs, for example, you can, if let's say you have all the components somewhere where you're confident, you have precipitation, you have runoff, and you have model ET, and you want to see whether your ET is good enough. And you can use the water budget as a validation, as an indirect validation. For example, in this study by Bhattara et al., they developed an ensemble surface energy balance model, and they compared it with other models over these Indian catchments. So, which was only for India, and you can see the NSEP, their model does a fairly good job. The first one, yeah, and others for all the catchment they are just far away from zero, so they were not able to close the water budget. So you can validate. You can actually use it for estimating ET, isn't it? If you do not have any ET estimator, you do not want to do it using remote sensing data of let's say land surface temperature and other things, canopy and all that, then you may actually use the water budget if you're confident about your runoff and precipitation and total water storages from Grace, then you can estimate ET. And Xiong et al. In 2023, they did that. But you remember the problem with the Lehman paper? There are so many options for choosing precipitation runoff that that you end up with a lot of combinations. So what they did, they explored the full spectrum. They got 4,669 combinations, and they said, okay, let's take the mean and median, and then see if that makes sense. So they have given the ensemble mean of ET realizations from these many combinations, but they have a large spread. So uncertainty is a problem there, right? Now, to tackle this limitation, what we did, we used a Kalman filter. And so what we did was we used each combination, ET from each combination as an observation, and that kind of can update the state variable, which is ET here. And when we did that, we found that uncertainties went down, and we were able to get very good results. For example, look, this is 2003, and on the left hand side, that is A and C subplots are from era 5, and on the right hand side they are from our approach. So the top is the ET value and the bottom is the uncertainty. And you can see uncertainties are much higher for era 5, but our uncertainties are much lower. And the Kalman filter solutions, they stabilize. What we need is uncertainties also in all the budgets, all the budget components. And we can only get up to 96 combinations for which we were able to get either formal uncertainties or some kind of uncertainties. Good thing was our results stabilized only after 30 combinations. So we do not need 90 odd combinations. So 30, 35 is good enough, and you can have a reliable ET estimate. Another way to look at it is using this figure, wherein we have taken the ET time series for several catchments. Yeah. And you can see in the bottom plot, the peak of ET is not captured very well by ERA. And this is because they only take precipitation and the radiance or the radiation as the major driver for ET. But in India, in Ganges especially, the C plot, the C subplot, it is for Ganges. And you can see that there the agriculture part is a common practice. So they grow paddy, and for that they already flood the fields in June. So we can expect a higher evaporation in June, but for them it only happens when there is a monsoon, and monsoon for the Gangetic plain hits in July. So early end of May and June is where I think in reality there's a lot of evaporation happening, but it is not captured by ERA 5 because it does not capture irrigation. But when we use the water budget approach using Grace, we are actually able to capture it. And we can actually justify it, or we can validate it using a model based, wherein we, in the model realm, we actually, we have the WIC model is used with irrigation capacity. So it's a realistic simulation wherein we say, okay, let it be ponded and irrigated for this season at this date. And when we do that, our results match very well compared to ERA. So this is again, I think, a good way to say that, look, if you use geodetic data such as Grace, then you are able to capture human interventions as well. Yeah. Okay. I'll just brush through some cool applications of Grace. I think I love this when sea level fell, by Carmen Boning et al. It was the La Nina event, 2011. And there was a steep fall in sea level, right? And everybody was puzzled. Why? And then using Grace, they could show actually there's a lot of water storage change, a positive anomalies in Australia and in northern part of South America. And this explains why there was a steep drop in the sea level, right? I would really encourage you to go and read this paper. This was an amazing paper. Then polar motion and climate change. The poles are, because of the conservation of angular momentum, we can, the mass distribution of the Earth, if it changes, it will also change the rotational axis. And this is what has been shown by Adhikari et al., that the low frequency polar wander is related to mass distribution. And if you use Grace, then you are able to explain the sudden change in the direction of polar motion since 2005. And this again, I think, a great paper to demonstrate, uh, that okay, how grace is a global observation and can help us understand and explain polar motion. Then we estimated GIA from grace data. Now you might have heard GIA is a process wherein uh, the last glacial cycle, even New York was under 4 kilometers of ice. When it receded slowly and slowly, and due to that load, the Earth deformed. And when the ice age receded, the ice was lifted, and now it's rebounding back. Yeah. So that process is called GIA. And we can use GRACE and GNSS together. We can combine these two geodetic data to estimate what could be the GIA rate today. And this is what we did in this paper. Simply, we took the mathematical functions representing these processes and then solved them in a data-driven sense, and we got this map. The beauty of this product, of this GIA data, is that if you use a model GIA data in Alaska, you get very, very small signal, right? Because probably the little ice age is not represented well, the viscosity is not mapped well, and so on. And you get some spurious signal in the middle of Canada. So a GIA signal is in the middle of Canada, which when removed results in a negative trend in total water storage in GRACE. And if you talk to hydrologists from Canada, they're like, we can't explain this signal because there's nothing happening in the middle of Canada. But when you use our product, actually, this -2 millimeter per year of hydrology signal in Canada disappears, and in Alaska we get a 5 mm per year of vertical land uplift, which has been observed after correcting for tectonics by several geodesists. I'll go towards the future of hydrogeodesy. I think there was this very good paper, 23 unsolved problems in hydrology, and these were the subtopics. I would say the broad topics or broad fields in which they think uh, these challenges lie: time variability and change, space variability and scaling, variability of extremes, interfaces in hydrology, which also includes groundwater, measurements and data, modeling methods, interfaces in society. And believe me, in all of these, geodesy can contribute and has contributed. Yeah. So let's talk about scales for a moment. Now, I have plotted here three geodetic techniques and their scales. So GNSS is a point data, GRACE is coarse, altimetry is finer than GRACE. So you can see on the x-axis we have different spatial resolutions. On the temporal, you can see GRACE is a couple of decades old. It starts at monthly. GNSS is daily, and in certain regions we have even more than decades of data. Altimetry is sub-monthly, maybe sometimes 10 days, 16 days, and it is more than now approximately 3 decades. You can say more than 3 decades now. Yeah. So this is the spatio-temporal scale. The axis is right. They're highly nonlinear, and you can see where we are. So where they kind of GRACE, GNSS, and altimetry. Sometimes if you can use to complement them to each other, then you can do amazing things like we did with GI, right? But I think as time passes, we'll improve on it. But there must be an effort to fill the gap as soon as possible. For example, this is the dotted box is where we want to be. We want this space to be completely observed. So you can also downscale GRACE. For example, GRACE is not very fine. So for fine grid, for example, for GRACE, we can downscale. And there are several papers. So in one of the papers, we downscale GRACE, ensuring that there's a conservation of mass. And the moment we downscale, we could see actually the river channels in Amazon and so on. So this was very, very satisfying. Okay. Um, and there are so many tools to do that. Then understanding drivers of change. For example, if you look at the GRACE trend, so the orange line is the interannual signal in GRACE, and the red line is the fit, a linear fit to that interannual chain, year-to-year chain. Yeah, these are two catchments, Indus River and Death Valley catchment in the California. They both have exactly same trend over the GRACE period. Yeah. So you would say, if you plot the trend in GRACE data, you would say, well, these two regions are having steep decrease in time series, right? And probably they both have severe total water storage chain. But the moment you put past into perspective, now this is from model, from GLDAS, natural variability from GLDAS. The moment you put that, you say like, well, I think the trend for Indus is much, much more severe than compared to Death Valley catchment. Yeah. And this is something which we published in ERA in 2021. And we actually gave a new metric that helps us demarcate or those regions which have severe trend. So if the top is the trend map, and you can appreciate that there are dark brown, that is negative trends, but you may just focus on the middle, saying, well, they are suffering more. But if you put the past into perspective, then you can see that, well, there are many regions where there was a small change, a small linear secular change, but still they are in a lot of distress right now. Yeah. So this is what we also did. But again, in this study, what we used was for the past something from model, right? And I already said in the beginning that models are not perfect, right? So many people have tried to reconstruct TWS. Said, okay, let's say we have TWS. We have for now, but we do not have for past. So can we reconstruct? And there are statistical methods, machine learning, water budget based reconstruction. And I'm just going to show you a couple of slides with different reconstructions. Yeah. And you can appreciate that, well, they do not agree with each other. They have some trends that are really, really unrealistic. For example, look at the green. It starts at minus 200 and suddenly it stabilizes in 2000 and post that era. But before that, so going to the past, reconstructions are doing a horrible job and there is no explanation behind. So we currently were looking at better options, such as we are using causal inference, and maybe we need a better model, a better system model would do it. I really do not have the perfect answer, but probably in a year I will have. So we are trying to reconstruct the water storage. Yeah. And this lengthening of the time series will also help us understand the role of climate change in modulating to TWS, which also solves another problem. And also the closes the holy grail, or and this is the holy grail of hydrology, right? Okay, so I think more interdisciplinary research is expected in the future. One of the major, I think, questions that I always get from hydrologists is that, okay, both climate and humans are responsible, right? Can we somehow attribute the change we are witnessing now to climate and to humans? And how can we do that? But it's this question is the answer to this question is still elusive. But I would say maybe there is hope that, if we use geodesy more, we might be able to see it more. Now, scales at which we can optimally separate the impact of humans and climate change. I think this is something that we have to understand. Geodetic methods are great, but they have limitation in scales in terms of spatial and temporal resolution. And if we acknowledge that, then probably we can do a better job. And we can also address the problem of scales in hydrology. And finally, I would say the upcoming missions such as MAGIC or SWOT, which is currently in orbit, an improved GNSS network will only make hydrogeodesy more relevant in the future. And I would just like to acknowledge a lot of people. I think this is not the end of it. There are many more people uh, through whom, through discussions, or maybe even collaborations. Some of them are my teachers, my colleagues, and students, and so on. I have learned a lot, and this keeps me excited. Yeah, for the next foreseeable future as well. With this, I'll close this talk, and if you have any questions, please ask. Thank you.
Great. Well, thanks so much. I see some applause in the chats here. So we really appreciate your nice overview there of so many different aspects of hydrogeodesy. And so now the chats are open, and you're able to unmute yourself if you have a question to ask. But as you're sort of coming up with your questions, I will just start with the first question, which is just thinking back to some of the motivations you started at the beginning of your talk in terms of actually using this information to help planners, about people who are thinking about using this to improve the situation or water usage. Do you have any comments about that in terms of how you've seen it used, what you think the potentials are, what the challenges are to sort of using hydrogeodesy to be actionable and to make a difference in future water use?
Yeah, so I think the example of India was a great one. Yeah. So after that Rodel paper, there were many investigations from the government itself, and then there were policy changes. For example, prior to that, there was free electricity given by state governments to farmers to help them irrigate their fields, and then they were like, well, maybe this is not the best of the idea. So they limited the hours for which they will get the electricity for pumping water, and so on. Even in some regions, they abandoned that, just completely said that no one should be allowed to pump water during these seasons, and so on. Um, and there was also a shift in the crop policy, which crop should be promoted in these water scarce regions. And this has actually led to a recharge. If you currently plot the Grace Time series, the latest one in that northwest of India, you'll see the levels have slowly come up. The problem is not about the water quantity now. The problem is water quality because of the farming, let's say, standards followed there. Sometimes we see a lot of pesticides and heavy metals in the water. So that is much more worrying sign right now. But the same thing goes with Lake Victoria. In Lake Victoria in 2005, journalists broke the story that they are releasing more water than allowed. Yeah, to the River Nile. And before that, you can see if you look at the Grace time series from 2002 to 5, it's a steep decline. And when this story broke, then all the because it's a transboundary lake, three countries are partners in that. They all sat down and they were asked to enforce the treaty that they signed on. And then the lake started to stabilize, and it stabilized within 3 to 4 years. So these are a couple of examples I would say where geologic data sets, altimetry and Grace has helped a lot. And yeah, researchers like us, when we publish something, it's taken up and it becomes an actionable item.
Great. Thank you. That's a great answer. Any other questions anyone has?
Sorry if
No.
I
I
was
have a question.
a bit fast, but yeah, I think.
Yes. No, we have a question. Go ahead.
Yes, thank you for the great presentation. I enjoyed it a lot. I have a question about the part that you mentioned that maybe I understood it wrong, but correct me if I'm wrong. I think you said that you were able to extract groundwater by from Grace data without using any models. Can you explain a bit more about that? Thank you so
I
much.
think I said that you have to remove, no, you have to remove the soil moisture anyways. So soil moisture can come from ESA CCI products. That's one way. In certain regions where there are not major surface water bodies, or you are confident about the canopy water storage to be negligible. For example, in northwest of India, it's a very, very dry. It's desert, one of the deserts in India, Thar deserts we call it. And there are no surface water bodies, and vegetation is next to minimum. So you simply remove the soil moisture estimates from anywhere, and and you're fine. So in that region, you could use Grace directly, just use soil moisture retrievals from any satellite data, and you're okay. But let's say you take a region where there's a lot of biodiversity, there's a lot of surface water storage change, then you have to take into account those compartments as well. I think what I said, maybe without using any model was GIA. That we were able to estimate GIA, the glacial isostatic adjustment signal, in using just Grace and GPS. I think that's the complete data-driven part that I did. And if I have said something in context of hydrology, that was that the Grace data itself that we processed in my PhD, we did not use any information derived from a model to correct for signal leakage. That happens due to filtering. So you take level 2 data, it's very noisy, you filter it, and to account for the loss of signal, you correct it. So most of the people in 2013, when I was starting my PhD, would use correction terms derived from a model. So the error or the uncertainty in the model will propagate to the Grace results. And what I did in my PhD was I developed a method that was independent of any model, that only used Grace data itself to, to estimate what could be the signal loss. Basically, I used the once and twice filtered Grace data to understand how once filtered Grace data changes to twice filtered Grace data, and use that information to back propagate and see what could have been the real Grace data. Something like that I did.
Yes, I think it was the latter one that I meant. Yeah, thank you for the explanation.
Thank you.
Great. Other questions from anyone in the audience? Give people a second here. So we have a question in the chat from Estelle. Let's see. I don't know if can you see the chat?
Yeah. With INSAR now resolving both water load changes and groundwater change, do you think INSAT could be missing piece between the scales of GNSS? I absolutely agree. I mean, this is, I think INSAR has to come in. I have seen even research, but that is being done at regional scale. For example, the Western US, for example, I've seen for California, isn't it, Matt? By Susanna Wirth and Mansoor Sherzai, they use a lot of INSAR data. the coastal subsidence they have talked about. They talked about the impact of groundwater change and so on. And obviously, this would not only fill the gap in terms of scales in space, but also in time, if I think about it.
All right. Do we have any other questions for Brahma? All right, I don't see any other questions at this time, so let's just thank Brahma again for a great presentation. Again, the recording will be available online, and we appreciate you staying up so late in the evening for us.
Oh, no, it's completely my pleasure. I'm really sorry that I could not push it later because I know it's still way too early for many of you, and I think half of the US they might be even just getting out of their bed right now.
Well, hopefully they can just watch the recording, but it was a great talk. Thanks again.
Thank you so much, and please send your questions to my email if you have any. And I'm always looking forward to interacting and collaborating. So yeah, looking forward to it. Thank you so much, Matt, for hosting me, and thanks a lot for patiently listening me for so long. Thank you.